Hello again. In this lecture I'd like to discuss separation technology and how you can use it to purify components such as lactic acid or lactate once the biological conversion is finished. In order to do so, we will take the following approach. First, we will need to remove solid particles such as bacteria, which is done in a clarification section. Clarification is typically performed using techniques that were already discussed in the microalgae harvesting section: centrifugation, flocculation and filtration. After clarification, we will need to remove a large amount of water and thereby concentrate the product. The final step is obtaining a pure and water-free product, which will be performed in the purification section. So the remainder of this lecture is split up in two parts. First, we will discuss how to remove the majority of the water in an efficient way, and here we will focus on evaporation and filtration techniques. After that, we will look into precipitation and crystallization techniques for the purification approaches. We often use membranes for separation purposes. I already discussed microfiltration in the harvesting section, but membranes can also be used for other separations. Different membranes retain different products. Ultrafiltration blocks polymers such as proteins and polysaccharides, and nanofiltration retains small organic molecules. Reverse osmosis blocks salts. Now, the smaller the pore size of the membranes, the lower the water flux through the membrane. Also, the pressure drop that is required to perform the separation is higher in membranes with a smaller pore size than the larger ones. The oldest and most simple way to remove excess amounts of water is evaporation. Large industrial evaporators often consist of vertical tubes, also known as falling film evaporators. The feed is added to the top and forms a film on the inside of the tube walls. At the same time, steam is passed along the tubes, indirectly heating the film. By heating the film, evaporation will occur. The heat of vaporization is provided by the steam, which will condense on the outside of the tube walls, which can be recovered again. Once we have removed the majority of water, we need to start thinking about how to purify lactic acid further. So how are we going to use the physical properties of lactic acid to our advantage? Lactic acid and lactate both have a very low vapor pressure and a very high aqueous solubility. Most of the lactate in a fermentation mixture will form a salt with sodium at a neutral pH. However, please note that if the sodium is displaced with calcium in the case of lactate, the solubility will drop. The first approach that can be taken to purify lactic acid is crystallization. In order to induce crystallization, a saturated solution is required. Usually this is done by performing evaporation and/or cooling of the solution. Crystallization can occur spontaneously, but this is a very poorly controlled process. By adding small seed crystals made of the same material which you want to crystallize, crystallization will happen in a more controlled fashion. Afterwards, the solid material is often harvested using a centrifugation or filtration step. Bear in mind that usually a great deal of product is still dissolved in the aqueous phase and needs to be recirculated. Precipitation is a similar process to crystallization, but there is an important difference. During precipitation, oversaturation is induced by the addition of a compound. When you use precipitation, you are basically displacing the sodium with the calcium ion, which will result in a lower salt solubility. For example, the addition of calcium chloride to a lactate solution will result in precipitation, as can be seen in the movie below. As a technique to recover lactate, there are two things to consider. One, you will produce a salt byproduct, and two, the calcium lactate cannot be used yet to produce PLA, since it is in its salt form. Good luck with the assignments and see you next time.